Hello everyone. Today I'm going to be showing you how to create this interior where when you move it, it will generate a new interior that, while has some issues currently, does have a good starting base. Now this is not the final result, but as you can see, it has dividing things up by 3 walls. Each wall has a door and you can get into every single room with a single door in each wall. So you can see it has divided up this room. There's a door in here. You can get in this room as a closet. If I move this around, this is one of the issues that I have yet to solve, where sometimes it doesn't spawn the room. But as you can see, here's another setup where it just generates a door here, here, and here. So at all times, there should be a way into all rooms with small exceptions. But this is not the final product, but this is the beginning of it. So let me show you how to do this, as well as many things that I have learned along the way creating this setup, as this will be a tutorial on how to recreate this, and also a lot of information on the limitation of PCG, as well as some things that you can or should do differently just to get it working. So let's get into it. So here we are back to the old project that we started with the building. Now, again, if you're coming into this for the first time, I will be showing how to do this without all of this set up. It is not required for the interior. One quick thing I'm going to change is right now we have the doors randomly generate based on how many we have. But if I have one floor, one thing I noticed is the door vanishes actually, as you could see here. I'm not sure why, but it's a simple fix. Where we have this difference node, these 2 difference nodes to spawn the doors. So the doors are supposed to be right here, but they're not spawning. I found that it just doesn't like 2 inputs here for the difference. So instead of that, what I'm going to do is just detach these and then just attach this difference node. And then that solves the problem. So now it will spawn based on the difference of these 2 already combined instead of having to manually drag them out. Gets the same result, but now no matter if it's more or less floors, the doors actually stay. So with that, let's go ahead and just, for the time being, turn off the roof so that way we can see inside of it. And we need to get the interior going. First, I want to explain how exactly I am making this with a quick Photoshop drawing so you can understand how this is all kind of figured out. So we're starting out with the floor, which is made out of the points where it spawns the floor, right? So this will be a tile, tile, tile. So we have all the points for the tile. So we can use this information because we can use this to spawn walls. And the way we do that is instead of spawning the floor and then figuring out the distance around the points, we can take these points and say spawn a wall here and spawn a wall here. And each one would spawn 2 walls, right? And so in a sense, you get a full grid of walls. So by using this, we have the grid. But then how do we specify where we want the walls to be and where we don't want them to be? So the way we do that is by looking at all the points we have here, then picking a random one. So let's say it picks this point. So it picks a random point, and then it has 2 overlapping, one that is facing in this direction, one is facing in this direction. And from there, it will go ahead and look at every single point that it has in either direction. So if it picks this way, it will find this point, this point, this point, the point down here, and it will basically spawn a wall on all of them. After it does that, it picks a random one of these points, gives it a different density. So for example, maybe this one, and this is where the door will spawn. Then it goes and selects one of the remaining walls that is not the door and says, okay, rotate the point 90 degrees because there's 2 overlapping, one that is not rotated, one that is rotated. Pick the other point and then do the same thing. But if we did that, and let's say it picked the point right here, right, it would do a wall here, here, and go all the way across and in this direction. And we don't want it to go also in this direction. We want it to only go in one direction. And the way we're checking that is we're looking at how many points are in one direction or the other direction. And if one of those directions has more than the other, then only spawn it in that direction. And so effectively, then it will do the same thing. It will spawn the points here, put a random door in one of these points. And then if needed, it can repeat. So it can pick another point. And then let's say this is 2 away. And then one of these would be a door. And so, so you're able to kind of divide this place into a big section, smaller, smaller, smaller. And it's not a perfect setup, but this is independent of any shape you originally had. So you can use this for any kind of grid setup to just break it up. It can be done for interiors, it can be done for something else, but this is kind of the methodology that I kind of came up with that should be working. It does have some issues, and there's also some things with limitations of PCGs I've learned in terms of randomness. So, but this is how the process will be. So with that out of the way, let me show you how this is all kind of set up inside of Unreal itself. So here we are back in Unreal, and we're just going to go ahead and get started with taking our original spline sampler, which is just doing the interior, as you can see. And like I said, we need to take these points where we have the floor tiles spawned, and we need to rotate them 90 degrees and keep the original. So the way we're doing that is by taking this, and I'm going to do it right up here, and grab a transform points. And I'm going to just double click here to make another point, and then I'm going to grab another transform points. One of these will be rotated by 90 degrees in the Z. So effectively, if I sample this, we have 2 points exactly on top of each other. So that's exactly what we want, because if I was to take one of the walls, so if I took this, duplicate it here, and I plug this in, you could see that we get all our walls now spawning in both axes, which is perfect, which is kind of what we want. Of course, we're not going to want it to be in this manner, but for now, this will be fine. So from there, I'll go ahead and just merge these two. So that way we have one node that now can sample both of them together, overlap. And I'm going to do a density remap. And all I'm going to do is say in 0 to 1, out 0. I just wanted to remap it all to 0. And the reason is I found it's easier when I'm going into my custom node, which is going to be appearing right next to it. It is easier for it all to be 0 from the get-go. I might integrate this into my node later on, but for now, this seems like a simple solution for the time being. So let's get ourselves the custom node that will be taking care of all of this. So for that node, I'm just going to go ahead and duplicate the select random points node that we made before, and I'm going to call it interior walls. And we're going to change some things, starting with the node title override. Instead of select random points, I'm going to call it generate room walls. I'm going to compile this. And now if I go ahead and grab it and just drag it in, right, there's our generated room walls. Of course, it is not set up. So if I plug this in, it doesn't get us the result we want as of yet. But now we can go ahead and tweak this. So for this node, if I go to execute with context, we're going to change a lot of this. A lot of this we won't need, but let's go ahead and clean this up. So after this PCG points, we don't need the point count. We don't need all of this. Get rid of this. You can get rid of all of this and get rid of all this. So if I go ahead and delete it, so I'm keeping just the PCG points set members section. And in the end, I'm keeping this set points. So we're going to be using these two sections, but mostly everything else needs to be more custom. So I'm just going to go under edit, delete unused variables, delete these guys. And under here, we don't need indexes to select, index tracker, selected max points, point count. We just need these guys right here. So with that, we now have a nice clean setup to start with. Let's start with our first thing. The first thing we want to do is actually calculate if the point is the furthest on 2 axes. So if I come here and if we just generate this wall, you can see it is offset. So what we're going to actually need to do is do a transform points, and I'm going to offset it in absolute offset by -half of a wall size and -half of a wall size in Y. Now, what this does is it creates a wall against another wall. While the rest of the walls are perfectly in place, these guys are kind of overlapping, and we don't want these. So what we need to find is when we're selecting a random point here, I don't want it to select these points. If the point that it selects is the furthest in the X and furthest in the Y, then redo it. Pick another point. To do that, we're going to add 2 variables. We're going to call the first one, actually we'll go 3 variables right away. The first one will be wall segments, and this is going to be an integer that is exposed. And this will specify how many walls do we want to have. And the slider min max will have as 1, slider and value minimum will have as 1, and the wall segments minimum will have as 1 as well. And we'll have 2 extra variables, both of them being floats, and they're going to be just called furthest point along X and furthest point along Y. Because we need to know if it is one of these points, then we can go ahead and ignore them. So what we're going to do is just drag out these 2 into a set node. And because in our scene, we see we have moved it in the negatives. So if it is the most negative X or the most negative Y point, then go ahead and ignore it. I'm going to just put a very high number in here because effectively what we're doing is checking if it's going to be less than this, then do it something. So I'm going to take the PCG points and I'm going to do a for each loop and it's going to check all of them. Now to keep things clean, I'm just going to select all of this and I'm going to right click and I'm going to collapse to function and I'm going to call it calculate for this point. So that we're keeping it a little bit cleaner in our main graph. I'll open it up. And this part is pretty simple. So we're taking each point, we're breaking it to get our transforms, and we can go ahead and split the transforms and then split the location. So that way we get the XYZ separated out. And then we're going to go ahead and say, is the furthest point along X less than the point that it has chosen? So if it is less than, I want to go ahead and set the new point to be this point, to be the original point that it has now selected. So I'll just go ahead and plug this in. So now if it is picked, let's say along X, it is at 100, 100 is less than the very large number we have set up here, then it is going to go ahead and set it to be that number. The next one, it checks, is it further left? No? Okay. Then go ahead and keep it. But as long as it finds, it'll go through all the points and it'll find the lowest number X. And of course we do the same thing for Y. So for that, we're just going to add another branch. And for this one, even if it's false, we want it to continue on to check Y. And it'll be the same thing. I'll grab another less than node. So if it is less than Y, then go ahead and set Y to be this point. And there we go. So it goes through every single point, it checks it, and it stores the information for us. So this function is now done. We have everything we need here. So let's go back to our main graph. The next thing we need to do, now we know those points are the max, we need to pick a random point. So to do that, we can go ahead and get our PCG points. And then you think you can just use a random array element and you can get a random point this way. And then from here, you can go ahead and promote this to a variable and call it random selected point. So then we have a random selected point and we're good. Now, there is a problem with this, and this is one of the things why I want to go over my whole process, is this is not actually as random as you would think. So what I found is when I was using this method, it would always pick along the same axis all the time. So when I moved it and I regenerated it, one of the wall segments would just always maintain. And so I think this is tied a bit into the seed and positioning of PCG. So I found a more manual setup for a random point to give me a little bit more actually random results. So instead of using a random node, what we're going to do is get the length. And then from there, I'm going to get a random integer. And using the random integer, we can go ahead and use a get node. So we're finding a random point from this array using a random integer instead of a random array node to get the same result. And then we can plug this into here. So the result is the same, but the way we do it is different. And for some reason, this gives me a better randomness than the random node. So something to keep in mind. But now we have the point. Well, from here, we need to check, is that point actually the furthest point or it's not? Because if it is the furthest point, if it matches the information we got here, then we need to generate a new point. So we're going to use a while loop for this. So while something is true, go ahead and generate a new point. And for that, I'll just go ahead and duplicate the set point and just plug this in here. So while our condition is true, which is the point as picked either is minimum on X or minimum on Y, pick a new point. So for that, we go ahead and get our random selected point. We go ahead and break it to get all the information on it. Then we go ahead and split the transform, split it again. So then again, we have X, Y, and Z. And then from here, we're going to go ahead and check along against these points. So if it's furthest along X is equal to X, and same thing, if furthest along Y is equal to Y, and we go ahead and use an OR Boolean. Basically, if this point that it has selected is either the furthest along the X or the furthest along the Y, regenerate a new point until it has picked one that is not. To make our life a little bit easier, I'm going to go ahead and select all of this. I'm going to right click, collapse to function, and I'm going to call this furthest point check. And I'm going to make this a pure function. This cleans it up quite nicely. So now we go ahead and check if it's the furthest point. If it is, calculate a new one. But if it's not, we can go ahead and continue. Well, now that we have found the point, we go ahead and take it and we go ahead and break the point information, and we want the transform, and we're going to promote it to a variable. And we're going to call it random point transforms. And go ahead and complete it. Go ahead and take this random point that it has generated and store that transform information. And to clean it up, I'm just going to click hide unconnected pins, so that way it gets rid of all the extra stuff. But now we're storing that information. But we also need to find out if that point is rotated or not. So which direction it is going in, because that is very important. Because we can always keep checking if the wall is rotated or not, but it's easier to just check it once and then work off of that. To do that, all we need to do is get our random point that we just created, the transform, split it, and then we can go ahead and check the rotation if the rotation is equal to something. And if it is, then we can go ahead and just promote this to a variable called rotated wall. I'll plug it in right here. So if it is going to be rotated, so in our case, if it is rotated 90 degrees, because we're rotating along Z, then it will be a rotated wall. Now, for some reason, this doesn't actually work, and I'm not sure why. But if you drag out of this node and set make rotator and plug the 90 in here, then it does. I am not sure why, but that's what I have found. Also, this bottom value, if you hover over it, it tells you, but it returns true if A is equal to B within a specified error tolerance. So I just like to put like 1 degree here. So as long as it's plus or minus 1 degree, this will be true. This is just in case it does these kind of decimal points. Sometimes when you move an object, it will like to, instead of being at exactly 90, it'll be at 89.99999, etc. So this just takes care of that. So now if this wall is rotated, then go ahead and please consider it a rotated wall. At this point, we now can get started on the actual wall spawning process. So let's go ahead and grab our wall segments. And based on this number, we need to do a loop. So we grab ourselves a for loop and put the last index as our wall segments. And our first index will be 1. That way, when we specify 1 wall, it goes ahead and spawns only 1 and not 2. Otherwise, if it was 0, it would spawn 2. And for convenience, I'll go ahead and promote this index to a local variable. I'll call it wall spawn index. From here, we can go ahead and do a for each loop again, because for each of these segments, we're going to go through every single point. So let's get our PCG points and go for each loop. We want to figure out if we should be setting it to a density of 1 or a density of 0 based on if it matches our criteria. What we're going to do is convert this array index also to a local variable. I'm just calling this wall index. And then we're going to go ahead and get ourselves a branch that specifies if this condition is going to be true, we're going to be spawning it based on the parameters. So let's get our array element and we're going to break it. And from here, I'm just going to right click on this break PCG point and convert it to a function immediately to make it easier for myself. And I'm calling it condition check. And in my case, I'll make it a pure function and we can go ahead and open it up and get started on actually setting up our condition. So what we need to do basically is compare this point to our random point transforms. If they're in line with each other, then we go ahead and spawn it. Otherwise, we don't. So I'll take our transforms and I'm going to split the transforms and split the locations for both of these. And then let's start comparing them. So our Z, our transform Z, which is our verticality, is always going to be equal. In our case, because I haven't set it up to be multi-floor yet. But for the time being, assuming that I'm going to be setting up for multi-floor, we're always going to be checking also if the location of Z is the same. Perfect. We're going to need to do a few of these checks, so I'm immediately going to just grab an AND Boolean. So assuming that that is correct, and our rotation is the same, so go ahead and grab ourselves an equal node for the rotation. And again, I'm going to specify within 1 degree, just in case. So if it's on the same axis and the rotation is the same, it is now going to be true. So I'll go ahead and just on the end here, I'm just going to add a return node. And I'm just going to drag this AND pin right into the return node to generate a return value. And I'm just going to call it place wall at the end, because if it is true, it is going to place a wall. But now we also need to check the X and the Y. Now we have 2 different rotations and 2 different axes that we need to work with. And we need to check if it is rotated, then it will use one, but if it's not rotated, it will use the other. So let's go ahead and add an extra pin here. And we're going to go ahead and compare whether the Y is equal to the Y or the X is equal to the X, but entirely dependent on whether or not it is rotated. So the way we can do that is by using a select node. So if you just right click and search select, you get the default select node. And we need to get rotated wall and plug that into our index. And our return value, we can plug it into the AND. And effectively what this does is convert the inputs here to true or false. So if it is false, if it is not rotated, then go ahead and use the one that is comparing the Y. And if it is rotated, then go ahead and use the one that's comparing the X's. If the wall is rotated, it'll be comparing one. If it is not rotated, it'll be comparing the other. So that way, the ones that are not in the same rotation will be ignored. Great. But we also want to check if it is less or greater than, because as you saw from the demonstration, I want to only spawn it on one side or the other. So for that, what we need to do is add another pin here. And I'm going to just duplicate the select node. And what we're going to be checking is if this is the first wall or a consecutive wall. Because for the first wall, we don't want it to end anywhere. So for that, I'm going to add a new input here and call this wall spawn index. And that is going to be an integer. And I'm going to get wall spawn index as a variable here, plug this into our select node, and our return value is going to go into this AND node. And in our main graph, execute with context, we have our wall spawn index. So we can go ahead and either drag this over or bring this over. There we go. And we can plug this place wall immediately inside as well. So going back into the condition check, if the wall spawn index is greater than 1, it will be checking everything. But if it is not greater than 1, which means it is the first wall, just mark it as true. So that way, it doesn't care about anything that comes past this. But on all future walls, on wall 2, 3, 4, it goes ahead and checks it. So what we're checking is, first, which side we're going to be on. Is it going to be the left or the right? And we haven't set that up yet. So I'll go ahead and add a new variable and call it wall side. And this is going to be a Boolean. I'm going to grab our wall side. And again, I'm going to duplicate the select node, make it easy for myself, and plug this in, and plug this into true. Based on which wall side it's going to be, is going to compare different things. We're going to set this up in a bit. So if it is going to be false, we're again going to compare it to whether or not it is rotated, because it also matters. The left and the right will change if it is rotated in one direction or in the other direction. So you can see we're getting just a chain of Booleans here. There might be a better way of doing this. For the meantime, this is how I decided to do it. But if you have suggestions on how to easier clean this up, please let me know in the comments below. But let's start with our false first. For our false, what we're going to be checking is if our random points x is less than our points x. And if it's true, if the wall is rotated, instead of checking the x, we'll be checking the y. The random transform goes into the first slot. The original point goes in the second slot. Plug that into true. And I'll go ahead and move this again to the side. Try to keep this a little bit cleaner, but there's really no way of keeping this fully clean. And if the side is the other one, then we can go ahead and do the same thing, but instead of this time, it'll be greater. But as you can see, effectively what we're checking is that the verticality is the same. It is rotated in the same axis. And then it checks if it is along the same line, whether along X or Y, depending on what rotation it is. And then if it is the second or third or fourth wall, then it goes ahead and checks, is that wall going to pick which side? So this is where our wall side is. And one thing I actually noticed is I get a better result occasionally if I have the Y here on less or equal to and the X on greater or equal to. So just swap these two out when you're creating yours. That's the only thing I noticed later down the line. So to make my life a little bit easier, I'm going to actually expose a few more nodes here. And this is just to kind of as a pass through. So what I'm going to do is I'm going to expose density. I'm going to take density from here and I push it through. And I'm going to push through the point all the way through. So I'm just going to reorder these, put PCG point, and I'm going to call it PCG point out. Keep it on density. And this is just a little bit easier because now I can grab from here the point instead of all the way from back here. And I already have the density exposed. Because from here, we need to get our set members node. So if it is true, we're going to set members and we're going to set the density to 1. And this is where we want the point out. If it's false, we're going to duplicate this and we're going to keep the density of what it was. And this is why I set everything to be of 0 density right before this custom node. So effectively it is going to keep it at 0, or when we go through this loop multiple times, if there was a wall there, it maintains that there is a wall there. But for our index, we need to go ahead and grab our wall index. So let's grab you, drag you over. And to clean this up, I'll just kill one of these so we can have this all nice and clean. The reason we have this also split up is we want to actually make a note of all the indexes where the actual walls are being spawned. We need to know where these walls are because we need to use that information to pick one of them to be a door. So for that, we're going to go ahead and make a new variable. And I'm just going to call this wall index list. And this is going to be an integer array. And we're going to grab it and add our index from our wall, but only when it has placed the wall with density 1. So effectively, if it has passed the condition, it has made the density to be 1, add that index to this list. That way we know for sure that this is where we go ahead and place our wall. So once this is complete, we want to go ahead and just take this information again. I'll take you and just duplicate it here because we're going to be setting the points now based on our wall index list. So we can go ahead and grab our wall index list. And again, for the same reason as before, the randomness seems to be not quite that random. So let's duplicate this over, plug this into our get node. Feel free to experiment with the just random array item. This is a much more convenient node, but again, it just was not getting me the result I want for some reason. We're going to get our random wall index, and we're going to get our PCG point, and we're going to get that index. So that index is what we're going to be setting the members of. And we can go ahead and plug in our completed in here. And I'm just going to set it to 0.6. It's just a value that is different compared to the 1.0 for the walls and compared to the 0 where there's no walls at all. So you can pick any number in between as long as it's nice and convenient for you to kind of filter out down the line. But as for the index here, we just go ahead and grab the same index, bring it over. And then to make sure that the future walls do not get spawned off of this, the same index, because we don't want to have a wall intersecting where there's a door. Take the wall index list and I just go ahead and remove item, and I go ahead and plug this item in here. It has removed that point as a starting location. From there, we can go ahead and add in our completion. Just go ahead and grab this and we can move it over to our original for loop. And when the for loop is done, it is going to set the points, take care of all the tag data, and plug this all in as we need. But now we have this grid, and of course, we're still keeping everything here. Nothing has changed, but if I was to detach this transform points and sample our generated walls, you can see that it has actually culled things. So what we need to do is get ourselves a density filter, and we can go ahead and filter between 0.5 and 1. That's fine, the default, because it will filter out anything that is a black. So if I plug this in and then rebuild it, you could see now with one wall, it is going to go ahead and cut it up. Now it is spawning everything to be the same because that's how we have it currently set up. So what we need to do is change the order of this. So I'm going to do transform points first. Then I'm going to do a density filter. And instead of filtering out everything, I'm going to filter out like 0.7 to 1. And that is where we're going to keep this door for now. And I'm going to also filter out just between 0.5 and 0.6. I can do exactly 0.6, doesn't matter. And I'll just, for now, grab our door from here, plug this in. And if I rebuild this, you can see it is now dividing this wall and keeping one of these as a door. And each time it picks a random one. So effectively, we now are creating 2 rooms. That's great. None of these are appearing on the wall itself, on either of the edges. So this is working beautifully. So now we need to set it up for multiple walls. And we need to check which direction it's going to go when it does find one. So what I'm going to do is I'm going to just take all of this here after this for each loop, and I'm just going to scooch it over, grab all this, scooch it over, because here we need to go ahead and just do a quick sequence node. First, it is going to check if the number of wall segments is not equal to 1. Then it is going to go ahead and continue on. Because if our wall segments is 1, then we're good. It is currently generating what we want. We don't need to do any other math. We don't need to pick another point. We're perfectly happy with it right now. But if it is now the second wall segment in this loop, the third wall segment, etc., then we want to generate a new point and calculate everything we need. So to select the random point we need to go ahead and do the same thing we did here. We need to basically take all of this. We can take it and duplicate it over because we're now grabbing our wall index list and getting a random point on that list as we did before, but this is going to be our new starting point. And from there, we're going to set our random selected point to be this and convert it to be true. And then we need to go ahead and do a while loop one more time because we need to check while this has selected something that is going to be at the edge or not one more time. And for that, we have our furthest point check. So we can just plug that in, which is very convenient. So now when it is going to be false, I'm going to go ahead and have it still generate a new point. We can plug this in. But let's say it has picked a point, but it does not work, right? Let's say this point doesn't work. So what I'm going to do is after it has selected a new point, I'm going to take our random index list and I'm going to remove item. And instead of dragging all of this all the way through, I'm just going to take this and I'm going to duplicate it here, plug this in, and then I'm going to remove this. So that way, when it does it one more time on the second loop, it does not check the exact same location. But on the off chance that somehow something fails and it has gone through everything and it still hasn't found it, we need to have a fallback plan. For that, what I'm going to be using is just a simple select node, and I'm going to plug this into our condition, and it is going to say if the wall index list, if its length is 0, then mark it as false to break out of this loop, because this while loop continues while it is true. But as long as it's not cleared out of here, we can go ahead and use our furthest point check. So this guarantees that we will never have an infinite loop, because eventually the wall index list will get cleared out, and our entire setup here will then be marked false, which means it will be going to complete. Now that it has completed it and has found a point, because even if it clears it out, it has selected a point at the end as something. So assuming that it has, let's go ahead and set our random point transforms. So we need to get our random selected point, and we need to break it, because we need to get access to our transforms. But we also need to rotate it, because our new point needs to be going in perpendicular to our original point, right? Because we always have 2 points, one going one direction, one going in the other direction. So we need to go ahead and split our transforms here and split our rotation. And then we need to grab ourselves a make transform node. And again, for this one as well, split the rotation. So I'll just go ahead and move this out of the way so we can set this up. So our location is going to be exactly the same. We're keeping the location 1 to 1. Our scale is going to be the same. We are not changing that. Our X and Y is going to be the same. The one place where we're changing is the actual rotation in the Z axis. What I need to do is grab the rotation Z, and I'm grabbing a select float, and we have our rotated wall Boolean. So we grab that for a pick. So if the wall is rotated, it'll be 0. And if it is not rotated, it'll be 90. There you go. And this will be going into our random point transforms. Make it a little bit nicer. I'm going to right click on this, collapse to function. I'm going to call it rotate point. And I'm making a pure function. Just call it rotated point transforms. So now I have to clean it up just a little bit more. But of course, I need to also set that the fact that our rotated is now reversed. So I'm going to grab our rotated wall Boolean, and I'm going to be setting it as not rotated wall, not Boolean, plug this in. Because we have rotated the point, we also need to make sure that our function down here, our condition check, that is checking if it's rotated, understands that it is now no longer rotated. So we just go ahead and set it to be not rotated. And after which we go ahead and take our wall index and clear it. Because otherwise, when it's going to go into our next loop, it'll keep adding, but it'll maintain the original points. And we want to clear it so that way it is nice and clean. The final thing we need to do is this wall side, right? We have our wall side here, but we don't have any way of calculating it. That is the next thing. And should be the last thing we need to do. For that, we can go ahead and grab our PCG points and do a for each loop, because we're going to be checking each point. And I'll go ahead and plug this in. And just from the get-go, I'll go ahead and right-click on this for each loop and collapse it to a function. And I'm just going to call it calculate distance to edge. Okay, let's go ahead and open it up. Array, I'm going to just rename to PCG points. So that way we know what it is. So effectively, what we need to do is similar to what we did in our condition check, which is we need to check based on the rotation of the object, whether it has more points in one direction or in the other direction. If it has equal amount of points in both directions, then it doesn't matter. It just picks the first one by default, and that's fine. So it will prioritize one direction over another, but of course you can set it up where it just randomly picks a different one. That is entirely up to you. For us though, what we're doing effectively is just doing a big branch check one more time. For that, we need to go ahead and grab our points and break it. And again, break our transforms and break our location. And we need to get our random point transforms and split that, and split our location, comparing the both. So we're going to make sure that first of all, that the points are equal in rotation. That is always a good thing to check. And then we're going to grab ourselves an AND Boolean, plug the AND Boolean into our branch. So now we need to compare X to X and Y to Y, but it will depend on the rotation. So what I can do is grab ourselves another select node, and based on whether or not it is a rotated wall, plug that into our index. We're going to check from our PCG point true, false, or true being false being X, true being Y, and the same thing from the other one. So if I duplicate this rotated wall, false being X, true being Y, and we need to compare these two if they are equal. Plug that into our AND node. So if our X's are equal or our Y's are equal based on whether the wall is rotated. And I can just kill one of these to clean this up a little bit more. Perfect. So assuming all this is true, what I want to do is compare the float. So if I right click and search compare float, this is a nifty node that allows me to, based on the input and something to compare it with, I have a greater, less than, or equal as options. Now our input is going to be another select node, and it is going to pick X when true and Y when false as our input. And the reason these are flipped from these, right? Because these are going to be matching. We want them to match, but the other axis will be either greater or less than. We need to know. So we go ahead and take this and duplicate it, and it'll be the same thing. So Y will be in false, X will be in true, and that is what we're comparing it with. If it is greater than, we'll count on one side of the wall, and if it is less than, we'll count on the other. To do that, let's add two local variables. They're both going to be just regular integers. I'm going to call it wall side A, and I'm going to duplicate it and have wall side B. What I'm going to do is grab wall side A and wall side B, and depending if it's greater, I'm going to increment it, and same thing here. I'm going to wall side B, increment it if it is less than. Now these are local variables, so I don't need to clear this. When it goes into this loop, they automatically get reset to 0. But once this loop is completed, we want to go ahead and check which one is which. So I'm completed. I'm going to add a return node, and then I'm going to grab wall side A and wall side B, and I'm going to just return if one is greater than the other. So if wall side A is greater than wall side B, then that is going to be one side, and wall side B is greater than wall side A. Or if it is the same, it will go to the other side. But we're pretty much done. So if I go here and if I regenerate this, I get a different wall. And right now it's set up to have one wall. And if I go to our building, I go to generate room walls and I set 2 as our wall segments, and then I go ahead and just move this around, you could see it is jittering 2 walls. Now, occasionally, as you saw, is actually picking the smaller distance actually here. So you know what? Let me go back to our calculate distance to edge. And let's swap this out to be B over A instead. And there we go. So that should be working now a little better. But you can see it is now dividing it up into 2. And if I just move this around, it is still occasionally picking the other direction. Clearly there's more points in one than the other. And occasionally it's still putting a gap for some reason. So I'm not 100% sure as to why this is. We swapped them, but clearly it didn't have an impact, because if I swap them back, and this is something that I've been trying to battle with PCG on. If I compile this, save it, and I set it to a grid, and I move it over and move it back, it's in exactly the same location. It has not actually recompiled it. In fact, I can even go here, click cleanup and generate, and even though we've swapped the information in the graph, it has not updated it. It is not recalculating it properly. So I'm not sure what is going on. But yeah, clearly our original axis was fine in most situations, so I guess I'll keep it as one over the other. But again, here, it should be picking in this direction, Nevertheless, it's still getting us a good result. So if I select 3 walls, now occasionally we have 3 walls generated. This one is missing, right? And it is missing this wall for some reason, and then it has created a sideway. Again, it's missing this wall. So which is why in my testing, I thought I could fix this by using this greater or equal. But for some reason, even though it is greater or equal to for positive x, that is not the solution, it seems. So it's still something I'm trying to figure out. But you know what? Nevertheless, each room does have an entrance. Each wall has an entrance that it generates, right? You can go in here, go in here, go in here. So you can get some interesting interiors using this. Now, this doesn't work currently for multiple floors. If I set it to be 2 floors tall, you can see it is not actually replicating it. In fact, there's also some bugs where if it doesn't find a wall to place, it'll place it basically at origin. So there's a wall there. So it's not 100% perfect. And as you saw when I dragged it around, I don't know if I can get it to recreate. There it is. It has picked a spot where it shouldn't be able to pick a spot. It's picked a spot along the edge. So I'm not 100% sure as to why it is effectively ignoring some of the condition checks at some points, and it doesn't properly recalculate. So I'm a little bit battling with PCG on figuring out why some things are working one way and then another way. There's probably a simple solution that I'm just missing, which is why I just need a little bit more time on this, and this is why it's not a full conclusion in this one video. It'll be a multi-part series on just the interior itself. But I hope this has helped you guys figure out how to do this, because again, because I originally start with just a grid, you can use this method to break up any kind of grid into smaller and smaller sections. Even if there is a wall missing, it is still an interior. It's occasionally, some modern interiors have walls missing. I can pretend, right? But yeah, that is going to be it for today. I hope you guys enjoyed it. This interior is definitely one of the most challenging things to do in PCG probably, and this is why you don't really get a lot of procedural interiors, because it's very hard to set it up where it actually seems like a proper interior with walls and doors that make sense. So I hope that this has helped you guys even a little bit. If you liked it, hit the like button, subscribe if you haven't, and I'll see you guys next time. Take care. Bye!